mentioned before, today we're going to actually start talking about binding. Actually, let me get my notes out. Shows you how old this all is. But binding. Okay, in general. Sorry about that. What is binding? It doesn't mean we're bound or bind. What does it mean whenever we say something is binding? In biochemistry based kind of stuff, like such as this. Not like there's a legal document being binding. Forming a connection. Oh, it's very peace, love, and understanding kind of thing. Yes, there you are. You're forming connection. What else? What else is binding? What does it mean? I couldn't hear you.
Joining.
They are joining. Mm-hmm. So what kind of interactions are occurring for binding? Well, actually, first of all, what are some examples? Let's just do examples first. Let me make sure that this is going to work. Oh, yes. In vivo. I mean, it doesn't have to be in vivo, but what's an example when we talk about binding relationships in biochemistry?
Like chemical bonding.
Chemical bonding? Between what kind of biomolecules? What are some examples of biomolecules? Water to... What?
Oxygen, H2O.
Well, so those would be a covalent bond of sorts, okay? Like hydrogen and oxygen make water. What about in vivo? What about some of the reactions in your body or something that requires binding? What's an example of binding inside your body?
DNA.
Pardon?
Binding DNA.
DNA binding to, what's an example?
I was thinking like when
Proteins, DNA and protein binding. Mm-hmm. There are lots of different proteins that can bind DNA. It's a good example. Or you can take RNA and proteins. What's another one?
Oxygen to hemoglobin.
Oxygen and hemoglobin. Mm-hmm. And so hemoglobin in biochemistry is Hb. Or you can say carbon monoxide. BPG for those who took biochemistry 1 last semester and binds to hemoglobin. It's another example. What about in this class? The name of this class would be for enzymes and substrates. Okay. What about an antibody? What do antibodies bind? Antigens. Mm-hmm. Okay. The generic term that I'm going to probably use here, rather than, so that way we can even talk about this with respect to not only enzymes and substrates, but many times they call them macromolecules, something really big, and ligands. Because this part of the course is true, because technically hemoglobin is not an enzyme. Okay, hemoglobin is a protein, and DNA is not an enzyme, but that's why. But we can speak about the same type of binding relationships and the equations and stuff. It's true for all of these. There are other, you can talk about, let's see, what are some of the ones that came up with, or like hormones, but the receptors, so that's from biochemistry. Transport of small molecules, or like neurotransmitters binding and trying to be transported across cell membranes. And the list goes on and on and on and on. Okay. And one of the reasons why I wanted to do this is rather than talking about E and S, we're going to use like M for macromolecules and L for ligand. Okay, just because that way it's a generic. Okay. Whoops, that's not what I wanted to do. Oh, I just wanted to put it in there. I don't know why. I had nothing. So how do you know when something's bound, actually? What's...
Strapped to your chest.
It stretches your chest, like you can see it. There's going to be some type of physical response there. Otherwise, it's going to be true for you're going to have that assignment coming in, not next class or so, but later on about the different methods that are used for binding. So yeah, this one we can physically see. There's a change. You can see that's Ike, the baby, and yes, he's got a bald spot from where he rubs his head. Because he just refuses to crawl. He's like, why do I need to crawl whenever I can scoop myself around on my back with my legs? So, and then it's my wife. Like the magic game. Okay. And so we'll talk about how to determine binding. So how do they determine? How are some of the ways that you can determine binding? What must be true? Like, how do you know if something is bound?
Does chemical change occur?
Okay, so there could be a chemical change. Especially, we like to, if at all possible, to use one that's maybe it's spectral, the scientific term they like to say spectrophotometric, like a color change. Or maybe a different type of wavelength of light. Sometimes you can't see it if it's UV or something like that. Okay, some type of physical or chemical change could occur. Something that you can measure. Okay, what else? This one's a little bit more difficult. And maybe you want to talk about comparing binding. Let's say that you got two drugs. Actually, it also ties into this. Why it's important. You have two drugs. So how can we tell if one's better at binding? Because you want to be able, many times, not always, but many times you want one that's going to be binding pretty well. If you're wanting something that's irreversible, you want it to bind really well, quickly, efficiently. So what's the tool, the measurement tool, so to speak, or the ruler in comparing binding? How do you compare binding between two things or more? Pardon?
Would it have to do with, like, I know that with a lot of binds you can compare energy changes?
You can compare energies.
KD.
It means you have to measure. It's KD. So the one that they use the most, we're going to talk, in fact, a lot of the equations we're going to be using KB for binding constant, the dissociation constant. And hopefully, when I show you an example of this, because there's no way, but I'll try to draw as best as I can, that it makes it more sense, like why they use KD for dissociation versus KB for binding. It has to do with units. Okay, and it is important. There are lots of ways. You can compare maybe the efficiency of binding between this enzyme with more than one substrate, or two drugs binding, the same receptor, or things like that. So there are lots of possible answers to this one. But one thing that you have to do, which is really obvious once we start talking about it, but not, at least for me, it didn't come to the top of my mind, is you have to be able to see a difference, or see or measure, I should say, the difference between, I'm going to abbreviate between what's free from that which is bound. Because if you can't tell what's free, what's not bound, the unbound versus the bound, there's no way that we're going to be able to measure any of these. And so that's one of the things. Usually, sometimes you may have to physically separate it. Okay. Experimentally. Sometimes it's just, there's a chemical change or a visual change that's given off. When it binds, maybe it changes colors. So then you can literally measure what the color is. But yes, and we say K, these are capital Ks. So for those of you currently in Gen Chem 2, those are thermodynamic constants. Thermodynamics always lets you know the ratio of something, but not how quickly it occurs. Little Ks are what tells you how quickly, but they don't tell you the ratio. That's why they're both important. But so there's the one for binding is called KB. The one for dissociation, it's called KD, and it really is the one that's more than often not used. No, more often than not, it is used. I said that so wrong before. You think I can speak English? I don't speak it well. So, okay. All right. And if you have any questions, just holler. I wanted to show, I was hoping this would come through. One of the reasons why that is important, this is ATP Synthase, if it comes through. If I can get an internet connection on my iPad today. So this is ATP synthase, which actually just is a good review for what we've did early on. Synthases are a class of enzymes. What are they going to do? What does the ATP synthase do? Synthesizes. It makes something. What does ATP synthase actually literally make? ATP. And it's not ATP synthetase, because ATP synthetase would be requiring ATP to make ATP. You know, so this is called ATP synthase. The one that I just wanted to show, it doesn't have any sound if I'm able to get it to actually work. Oh, you're gonna make me search all again. ATP. I like it because they show the different bonding. So these are the substrates coming in. There are two substrates that come in to make ATP, the ADP and intermediate phosphate. And they have 3 binding sites each time. So there's the 2 that come in, they literally get forced together after a proton goes through. And then they give you that little starburst look to make ATP, and then it will leave. You can clearly see the binding sites. This is based off of, the model is based off of crystal structure, let me believe. Then if they turn it over, you can see what's, it's called a stator protein. That's not that important. But it looks like it's like a little turnstile. That's what I always like to say. Like the little turnstiles at Disney or whatever, because it literally, as a proton, which isn't shown, so you can't see a proton, a hydrogen is so tiny. As it goes through, it turns a turnstile, and it literally forces ATP to be made. Because ATP, it's not energetically favorable to make ATP, it's energetically favorable Whoa! That's interesting. Can't do it to stop. Wow, they are really going to get that point across. Okay, so we ATP synthase again. But, ATP, you break it easily, it gives off a lot of energy. That's why our body uses it as the energy currency. But to make it requires that same amount of energy. Okay, and so that's why they literally force it to be made by ATP synthase. Okay, so that was just an example that I thought would be really easy to see. Literally 2 substrates coming together, then you can see the binding site and how catalysis occurred there to make ATP, and then it gets released. Okay, for those who go on to take biochemistry 2, it gets discussed in much greater detail later on. Okay, so now the binding in enzymes, and for all of these, by the way, they're specific binding. Usually, not always, but usually they have to be non-covalent. Whoops, misspelled it. Because you want it, with respect to enzymes, you're going to want it to be reversible. There are certain drugs where they're actually called suicide inhibitors, because it makes a covalent bond and it's irreversible and it kills off that enzyme, whatever it is. Aspirin is one of those. It's one of the ones that's common. Like just aspirin. One aspirin molecule will go in and kill off one enzyme, one COX enzyme. Okay. But usually we want it to be specific and reversible, because you don't want it to always bind. You want it to be able to be released, like what they showed there in the ATP synthase. Okay. All right. So, what are some of the interactions that can occur that are non-covalent? What's one? Let's think back to even Gen Chem. Probably Gen Chem 1, you can talk at least about some of these. What are some possible interactions that could be non-covalent interactions? And we discussed some of them earlier as well. What's one type of interaction that the macromolecule and the ligand would cause it to come together? And electrostatic, okay? So electrostatic interactions. That's a fancy term. That's actually not the term that usually gets used in Gen Chem 1, probably. And so what's like, if you were trying to describe electrostatics, and one of these are like about chemistry, that's a fancy term for what? What's an example of electrostatic interactions?
Ionic.
It's ionic. It's a positive charge and a negative charge coming together. The really old-fashioned term, they used to be called salt bridges too, because salts like sodium chloride, things like that coming together. But yes, electrostatic is technically the fancy term for it. Okay, what's another one? Hydrogen bonding is very important. Obviously, hydrogen has to be involved, but it's hydrogen, and the hydrogen has to be attached and interacting with, does anyone remember? Oxygen is the biggie in vivo. Nitrogen, and it's fluorine, and for fluorine, it's only for hydrofluoric acid. In vivo, you never have to worry about that, okay, because you don't want to drink hydrofluoric acid. Don't. But oxygen and nitrogen's around a lot. Okay, what's another type? It's van der Waals. Exactly, that's when I was wanting to. Okay. So there are van der Waals interactions. And then the fourth one in general that is actually many times forgotten about is called the hydrophobic effect. And this is because they want to exclude water. Okay, so if two things that are hydrophobic, they're going to want to exclude water, so many times they can come together. So I guess you can think of it as a very specific type of van der Waals. Almost the opposite of ultrastatic. Okay. And there's also the polar interactions, which is just a form of electrostatic, just not that's like a shade of gray, I guess you could say. Polar or between dipoles, so things that have like a delta plus or delta minus charge. Okay. All right. One other thing that has to do, not with the type of bonding, but I just wanted to put it here, and should be obvious, but people would often overlook it, is that binding must be stoichiometric. Which makes sense if it's going to be specific. And stoichiometric is like an awesome Jeopardy term. What does that literally mean? Like they don't ever use the word stoichiometric. Whenever I took calculus or in algebra, they never used it stoichiometrically. But they would say, what does it mean if we say it's got to be stoichiometric? It's balanced. What else? In order to balance it, what must be true? Like it's kind of hard to describe what is stoichiometry?
Making sure the moles on each side of the equation.
Right, it means that they are discrete in the sense that if maybe it's a 1-to-1, discrete ratios. It's probably something that they would probably think, right? It's like 1-to-1 or 1-to-2 or 2-to-3 or something like that. You can't ever have a half. Right? It's always got to be integers. You can't have a negative. You can't have -1 chloride ions binding to something. Okay. All right. And so that's why, and I mentioned this before, that I'll use M and L for macromolecule and ligand. We'll say it's reversible to make this, whoops, that's supposed to be an L, a bound complex. All right. In vivo, I'm just going to go ahead and do it. In vivo, you can think about, we've got a cell, Okay. Usually, and I'm sure that there are certain times that there are exceptions. Usually, do you suppose if we go back to think about the ligands or the substrates and the enzymes or macromolecules, which one are you going to have more of the concentration of in vivo? Usually. Are there going to be more ligands or more macro, or more whatever it's binding to? It's going to look like a philosophical question. So if we think back to that ATP synthase, which I wish I would, in fact, I keep on going. Do you suppose that there's more of the enzyme, the synthase, or are there more of the little ADP and inorganic phosphates floating around out there? More of the ligands, and that's true, usually true, okay? And that's going to, and the reason why I say that is that's going to make the math much more simple. Okay, almost always you got much more of the ligand than you do the enzyme or the macromolecule. I'm sure that there are certain exceptions to that, but usually we don't have to worry about that. Okay. So, okay. And so that's why we're going to do, those are the assumptions, like if you think back to like math and stuff, what we're going to say is the concentration of M is much smaller than the concentration of L. The reason being is that means that the concentration of L that's free is going to be approximately equal to the concentration of L total. Okay. And I'll probably start to abbreviate writing out total every time, just write it with a T. You can imagine you have like one ATP synthase and you may have 1,000 or 1,000,000 or more of the other molecules that come and bind it. And so that's why the amount, 1,000,000 minus 3 in 1,000,000 are still approximately equal. Even 997 versus 1,000, those are approximately equal. So that's a safe assumption to make. Okay, and so we have, I'm just going to rewrite this because I didn't, it's on the previous. It was on the previous slide. Okay, so we have a macromolecule such as an enzyme, and we're going to say at least one ligand. If you think back to balancing equations and stuff, there may be a number, a coefficient in front of that L, but right now we're just going to say, assume it's 1 to 1. Because we'll talk about what happens when it's not 1 to 1 later. And then we have the complex once it's bound. Okay, so for those of you in Gen Chem, have you started doing equilibrium constants yet? Because you mentioned getting ready to start thermodynamics.
At the end.
Pardon?
At the end last term.
Okay, so in general, this is just a quick review for those. If we said the capital K equilibrium, we always use concentration of products, depending on which direction you're going, divided by reactants. Okay, so we have products over reactants, and that's just the generic equilibrium constant. So if we are binding, are we going, in this example here, are we going left to right or right to left if you are binding? Left to right, right? We have two things coming together to bind as one. And so that means going left to right, always make sure, left to right, that's binding. And so we're going to give that a special, it's got a capital K, the subscript is B for binding. What's the product or products for binding? ML. And I apologize, if you think back to Gen Chem, they always use the brackets, the square brackets for concentration. The more and more I write, the more and more circular, in parentheses looking they become, but it really is a square bracket. Okay. What are the reactant or reactants for binding? M and L, and you multiply them. So it's free M, technically, and free L. Okay. By definition, the dissociation constant would be the exact opposite. It's the reciprocal of that. Okay, so that's why if you wanted to just to keep that in mind, sometimes, you know, you could write KD, that's dissociation, then you're going right to left, and it literally is free M, free L over ML. Neither one of these looks pretty. Okay, you know, in that sense, if we're looking at that, you have to know concentrations about these three things, and it's much more complicated than what it really is. So that's why mathematically right now we're going to show what it really will look like. Well, what happened to my watch? Let me take this out so that way you know. Okay. Okay, so this is just some other, the concentration of total macromolecule. Like I said, I'm going to abbreviate that as T. If we look up there in that, is that red or pink or brown or this color? What is this color? Red. For those of you who haven't come here before, I promise to be colors apart. So in that red equation up there, what is the? If we wanted to look at all of the possible macromolecules, what are they? What is M total going to equal? And so let's try to think of it in like a real world example. You know, and we're just going to say that we have guys and there are guys and girls, males and females. That's what I can't think of. Ladies, males and ladies. That way, M's and L's. Okay, males and ladies. And some of the males and ladies are in relationships with each other. Okay, but some of them are not. What would be the total number of males?
M plus M times.
Right, M plus ML. The ones that were not in a relationship and those that already have their girlfriend or whatever, lady friend. All right, so it's the same thing as here. Ooh, I've never used that example before. I have to try to remember that for future. Okay. Because what we're trying to do is trying to get everything down to as few what is it called? Variables as possible. I always forget my math terms sometimes. Like if this is just algebra, then, you know, rather than having X, Y, Z, and all these other ones, you want to try to just get down ideally to like X and Y, or just X if you could. Also, what we can do is we can actually use the definition. Let me get to the arrow. Yeah. The definition of either KB or KD. I'm going to use KB right now. The definition of this to solve for one of these. Usually the one that they solve or the one that they use is the bound. Okay, is the ML. So, in the red color over here, I'm going to solve for ML in terms of KB. So what that means is ML is equal to KB times M times L, right? Because all I did was cross multiply right here. So now I can actually plug and chug and get rid of this term altogether. So we have M total is equal to M plus what we just solved for, which was KB times M times L. Okay, and there's a reason why I'm doing all this. I'm going to get to that. Because we're going to see how we can determine binding just off of one or two things, rather than having all of this stuff here. It makes it so much more simple. Okay. And then where we get what KD is or KB, and then I can prove it. Just trying to give everybody a moment to get caught up. We can factor out the M, which they usually do. We'll save us a little bit of time. See, there's an M in both of those. So M total now is equal to M times, and that is a regular parenthesis, 1 plus KB times L. Okay. So let's go back to our whole idea of, because if I talk about macromolecules and ligands, maybe it's not as easy, but males and ladies that are together. All right. So if we wanted to determine the number, like the relative fraction, the fraction of the men in here that were involved in had a girlfriend or a wife, how would you do that? How would you determine that fraction? What is the fraction? I mean, enzymatically, not enzymatically, here we would talk about the fraction bound. I'm going to abbreviate it as this way, fraction bound. But if we were talking about this with males and ladies, or what's the fraction that are in the bound, ball and chain, bound to that? ML over MT, right? The number that's bound, the number of men that have a girlfriend or a wife, divided by the total number of men. Okay. So it's literally going to be ML over the total number. Well, guess what? We've already solved for that. We solved for ML right here, and we just solved for MT right there. So now we do our good old plug and chug. I'll change colors so that way it'll be a little bit easier. So now the fraction bound, which I don't know why they do it, but sometimes they call it the Greek letter nu, which looks like the little cursive V, just in case. Or sometimes they give it the little cursive F, so similar to function. ML was KB times M times L, and M total is concentration of M times 1 plus, that's supposed to be a 1, plus KB times L. Leave everybody a moment to get caught up. Right, because that was ML, ML. In total, can there's something that can easily cancel out? M. That's why we did all of this, so I'll use a different color here. That M cancels and that M cancels. So now we have fraction bound is equal to KB, okay, which is a constant. It's an equilibrium constant, times L divided by 1 plus KB times L. The KBLs don't cancel out, okay, because that 1 there. So think way back to, I don't know, is that algebra 2? Maybe it's calculus. Okay. So if you have problems trying to see functions, or you're used to seeing like y is equal to mx plus b, this would be y, the fraction bound, is equal to, we have, this is just constant, so it doesn't matter. So we have x over 1 plus x. Does anyone from biochemistry remember what would the shape of that curve be? It's not linear. What would the shape be? Let me make this all smaller and no, so if you have something that looks like this, y is equal to x over 1 plus x, and you're plotting y as a function of x, what does the shape look like? It's hyperbolic. It looks like this. Goes up, and at some point in time, it's going to peter out. That makes logical sense. Okay, and I'm going to talk you through it. So, and the reason why is there are only so many binding sites on that enzyme, or there are only so many binding sites on that macromolecule. Once they are all bound, you can't go beyond 100%, or the fraction is equal to 1. Okay? So what they would say mathematically, in calculus or in algebra, what they would say is they give you those limits. Here they say the limit as a concentration approaches infinity. Yeah, I don't know about you, but that was always really, that was not the easiest thing for me to picture. So I always have to kind of rationalize it. What that means is if you have so many ladies, you want to go back to ladies in a minute, there are a million ladies, and there aren't very many men. We're assuming we are being monogamous here, okay? Then it's gonna the fraction of men that has a girlfriend or wife will start to approach 1. It start to approach 100%, right? Because all of the men are taken, and I've heard many ladies making the broad generalities, seems like all the good men are gone, that kind of thing. So you can say, well, that mathematically proved that. But no. So this is said there are so few good men, I guess. Ladies, I'm sorry. Okay, and then mathematically what that says is, they say it this way. The limit as L approaches 0 would be, let me go back here. This would be 0, and 1 plus 0, 0 divided by 1 is still 0. And once again, if we go back to our real world example, if there are no ladies around, and once again we are being monogamous and heterosexual here in our example, in our real world example, then the fraction of men in a relationship there would be 0. Okay, because there would be no ladies, real ladies around. Okay, and that's what the graph looks like. If x is really little, it's going to be 0. If x gets really, 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 really big, it's going to approach 1 for the fraction bound for us. Well, not for us, but for macromolecules. Okay, so I'm going to just draw that a little bit bigger so that way I can draw on it. That's not what I wanted to do. Whoa, I left the 0 behind. Okay, so I'm going to draw this bigger. My old boss, when she taught this, and this is fraction bound, or the letter nu. This right here is the concentration of L. It looks like, and I'm not the best at drawing things, but I'll try. Something like that. And so this, remember, it's called an asymptote. That would be 1. If you're talking about a fraction, of course, this is 0. If they talk about percent, then it goes from 0 to 100. But it's supposed to be hyperbolic. Well, in my own, even though you won't be able to see it very well. Well, maybe. So she had printed out, she actually put numbers into a computer graphing program to show you. So let's say that KB is 1 times 10 to the power 6, which is unheard of, which would be about 1, what was a million? The units on that is called inverse molar. No one thinks, I should say no, I'm sure there are some people out there that can't think in inverse units. If you solve for it mathematically, it gives you these really, really weird units, okay, which doesn't make sense. So I'm going to make this a little bit smaller once again. How are we doing on time? Oh, awesome. What happens, let me change color. What happens when you are at 50% bound? Which, here in this example, would be something like right here. Okay. So what happens when you're 50% bound? Well, then that means the fraction is going to be 0.5. Right? That's, by definition, that's what it is. So we have 0.5, which is the same thing as 1 over 2. This is easy for me to show it that way. And then our equation that was up there in the green, I think, it says it's KB times L over 1 plus KB times L. So now we just cross multiply. So I'll give you guys a moment, to cross multiply. 1 times this, 2 times that. I'll change my colors so it's a little easier to follow. So 1 times 1 plus KB times L is equal to 2 KBL. So I'm not going to skip any steps. If we subtract a KBL from both sides, we would literally have it say 1 is equal to just a KBL. So far, that doesn't look like squat. Okay, right? But now, divide both sides by KB, and we get 1 over KB is equal to the concentration of L. It's supposed to be equals. What is 1 over KB also known as? 1 over KB is, you have to go way, way, way back. I think it's on the previous one, but in your notes. It's equal to something. What's the reciprocal of binding? Dissociation. So literally that means the concentration of L is equal to KD. So if we go back up here to the right, where I have this, where I drew this red line, and it comes down over here, that's the concentration of L. That point right there is KD. KD or KD will be in units that are easy. They're going to be whatever units your ligand is in. So things like molar, millimolar, micromolar usually. Maybe sometimes for proteins they say stuff like grams per milliliter, but regardless, you don't have to worry about these inverse units. Like, do you know what 1,000 inverse molar means? No. I don't, Whereas if I said, do you know what 100 millimolar is, I can kind of get it. It means it's 100 millimolar, 0.1 molar. Those are the kinds of numbers that we're used to using. So that's one of the reasons, and that's really a big reason why they like to use KD instead of KB when you compare binding. Yes, it's dissociation, but these are going to be in units that are not inverses. Okay, because that's kind of hard to think about in logical terms. So we've proven this, and not only that, but we've also proven here that anytime if we plot, or if you see a plot that's a fraction bound as a function of the ligand, or if we're doing this with enzymes and substrates, the fraction bound is a function of substrate. If you go over to the 50% and then go down, that's going to tell you the value. Another rule of thumb to have is this. And so for those who have me for organic chemistry, I liked giving what I call rule of thumbs, because that's the way I learned it. That's the thumb. Get it, rule of thumb. Is the lower the KD, or the smaller it is, the tighter it binds. Because by very virtue, you take a number that's really, really tiny, when you flip it over, it's going to be really, really big, right, for binding. And so that's why many times when they talk about drugs, they talk about the binding constants for drugs, they say something like 10 nanomolar versus another drug that's 100 millimolar. Well, that 10 nanomolar means that it binds, probably should have picked something that's really easy to do in my head. Well, it binds much more tightly. Okay, 10 nanomolar is 10, that's 1 times 10 to the power minus 8. What did I say, 10 millimolar, whatever it would be, to the minus 3. And so that's why you're talking about several orders of magnitude tighter. Okay, so that's why the smaller the KD, the tighter it binds. And that could be good or bad, depending on what you're wanting to use it for. So that's why that's our rule of thumb. And so on Monday, we're going to actually pick up with this and look like what happens. Right now, we're assuming it's just a 1-to-1 ratio. Okay, so what happens if we actually more than one ligand that binds? And there are examples of what that is. especially with metal ions, it happens a lot. And so what that will do to the graph and how to find it, and we'll also start talking about some of the ways that they actually measure this, and we'll do case studies. And so one of your upcoming assignments, which I don't have available yet, it'll probably be assigned sometime next week, has to do with binding. So you're going to look in the medical journals, or you can look at any journal. Most people will probably look in the medical journals and look for like an example of where they looked at binding. Maybe it's between two drugs, maybe it's an antibody to an antigen, maybe it's neurotransmitters, maybe it's something really, really bad. Like, well, I don't give away all the things. That I may even take that as some cases myself. Are there any questions over this? It's going to take a little bit of time. I am recording this. Knock on wood, it goes through. I've been having some problems with biochemistry, so that's why I try. Sometimes it takes it a while to turn them into YouTube videos and then upload it also on MyFire. That way, in case there's something that you've forgotten, then you can always just go back and say, no, I didn't say again on this or what we did. Are there any questions? So starting next week, we're going to start using and putting real-world examples into this right here. So like, what does that mean? I'll go ahead and I'll end class with prayer. So some books, I should say, remember, sometimes they use, it's a Greek letter, nu, for fraction bound. Sometimes they also like to use theta. It doesn't really matter to me which you use. Or you can just write out fraction bound, that's perfectly fine, as long as you define whatever it is. But all of this is equal to fraction bound. One of the reasons why they don't like to use the nu is because sometimes it's also used for velocity, or it looks an awful lot like the letter V for velocity, for how quick. So that's why some people like to use theta instead. But that's all equal to fraction bound. So I'm going to probably use theta right now because, and I'll try to always do that to be consistent. Because that's also what the biochemistry book for those who are in biochemistry lists use. But we had theta, and I gave it to you in terms of KB. But if you look at it in terms of KD, it's very, very similar. And so rather than to take the time to solve for this, I'm just going to give you the answer right now. I'll give you a moment to get caught up. Okay. Now we have it in terms of KD. And the only difference between KD and KB are that they were reciprocals of each other. So it's just that KD, once again, are using units that are much more simple to work with. And on that curve, that hyperbolic curve, it's easy to find, okay, since it's the concentration where you reach half max of whatever. Okay. And we showed that experimentally. If we look at this, besides having the KD in it, what's one other thing that you can notice that I put on here that you didn't see before? The exponent, the n. What does n mean or indicate? Think back to Gen Chem. This was Gen Chem. Forget about KDs and stuff, but if you saw the concentration to the n, or the x or the m, that concentration to some power, what would that have indicated? It's like the coefficient. And so the nice thing about looking at this equation, because it would take a little bit of time to try to derive it, is that this is actually assuming you can use this equation whenever you have more than one thing that binds. Okay, maybe now if n equals 1, it's just like what we saw before. If n equals 2, now we see a squared dependence on it because there are two things that's going to be binding, and so it's going to affect the fraction bound a little bit differently in 3 and so on and so forth. Okay, so this is one that also already has where n is equal to the number of things it's binding. Now, they do something that, okay. I don't remember the reason why first of all, I don't know who came up with it. Okay, this is going to be, ultimately we're going to be looking for something called the Hill plot or Hill coefficient. So obviously the person who discovered this, last name is Hill. But mathematically, when you see these hyperbolic functions, especially back in the old day, people didn't like to think in hyperbolic, so they used to have to draw all these by hand. So they always wanted to convert things into linear functions. Okay, they always said, let's convert this and let's turn it into a line, because lines are so, not much, so much nicer, okay, easier. Our minds can think of finding slope, of a line and things like that. So I don't know your math background, and I also don't know about the math classes here, since we're talking about things that are more biochemical or biological, if they explain this. But there are ways to turn a hyperbolic function into a line. Okay, and we're going to do this at least a couple times in this class, but that's why, I don't know who it was that was sitting there, some mathematician a long time ago was sitting there and they thought, you know what, why have a curved line when I can make it linear? So what they do first is usually they take what they call a double reciprocal of it. Okay. So they literally, because if you have A equals B, that's the same thing saying 1 over A is equal to 1 over B. Okay, so what they did is they just took the reciprocal of both of these. And you do this, because if you think back to the laws of fractions, you can't separate whenever you have, what is it called mathematically? I always need to look this up. I always forget. Like on the denominator, you can't break up the denominator. I know there's a mathematical term for this, but when there's a plus or a minus sign. Right? You can if there's multiplication or divide, because you can separate it out and multiply or divide. But you can't do that with a plus or a minus. There's a term for that. I forgot it because I just have. So that's why we couldn't divide it up to turn it to a line before, because there was a plus sign on the bottom, but now there isn't. Okay, so we can actually now take this and divide it up, where it's the same thing as saying KD over the concentration of L to the N plus L to the N over L to the N, which that simplifies, right? This goes down, this is equal to 1. So I'm just going to rewrite it. So we have KD over L to the N plus 1. So now it's starting to look, what's the equation for a line, if you remember from algebra? Y is equal to mx plus b. And so we can actually now take this, what I've written, and turn it into that mx plus b. Okay? And so I'll do that in a different color. Let me move everything up a little bit. And so that's the y. I know it looks weird, but that's y is equal to 1 over the concentration of L to the N times KD plus 1. So that's why this is called a double reciprocal plot, because now we can plot if n equals 1. So if we have something similar, something very simple, like in the simple case, if n equals 1, this becomes really, really simple. Okay. Because now we should see it. Y would be 1 over theta is equal to mx plus b. So the m would actually be kd. The x is 1 over L. And then the b is a constant. So that's why that's really simple. So if you plotted what's called the double reciprocal plot, you get a line. So if you plotted 1 over theta, 1 over fraction bound, and 1 over the concentration of your ligand, you're going to get something that looks like, it's not supposed to be so shaky looking, but it is. It's supposed to be linear. And then the slope here is equal to KD. So that's why it's called the double reciprocal plot. And we'll see this later on as well when we start doing some of the kinetic stuff. Because a lot of times, you can imagine enzymes only have so many binding sites or so many active sites, so you're going to get that hyperbolic function. But then they can do this double reciprocal. If you would rather see it linear, you can do a double reciprocal of what would be the y and the x, and usually in the perfect world turn it into a line. But what happens if n doesn't equal 1? Okay. Or if you don't know? That's, you know, if you don't know for sure, like we don't really know. This is a new system, and so what can we do? Okay, so it takes a little bit more math because this would be, if we go back up to the top green one, no, the bottom green one, 1 over theta is equal to, this is a constant, that'd be 1 over x to the n power, so it's not really a line anymore. Okay. So therefore is there a way to turn that into something that's more easy to graph and more easy to understand what's going on? There is, but it's ugly. Okay, so it's ugly in the in-between. The final product is nice and tells you a lot, but the in-between, ugly is my term, not scientifically term, but there is a way to do that. You have to do some type of log plot. Okay, and the reason why is if you think way back to algebra, whatever, anytime that you have like x to the n power, if you take log of that, the n comes down to the coefficient, so it becomes n times log of x. So that's why I say it's, you have to think probably a long time ago, and at least for me it's a very long time ago. All right, so, and that's why I had my notes all written out to where, in case I can't guarantee that I won't make any mistakes in rewriting some stuff, so you have to bear with me on this part. This one I'm going to turn smaller, over there. Okay, so because we're going to be focusing on this part right here, and so because I don't have it memorized, I have to work it out. That's why I was hoping I subtract 1 from each side, and I get KD or L to the N. Okay. That's all I did. I just moved the 1 over. But I want to simplify that y, what will become the y side. This side actually may look ugly, but it's not that bad once we take a log of it. It's the other one that's ugly. And so if you think way back in algebra, that's the same thing as saying 1 over theta minus theta over theta, right? Because theta over theta is 1. So therefore, that's equal to 1 minus theta over theta. Make sure that's correct. Yes. Is equal to KD over the concentration of L to the N. Now, Hill, the person who originally did this, wasn't starting from the double reciprocal plot. He or she was starting from the original definition, way back up there, that red. Okay, so that's why I'm going to have to do this. I'm going to have to take the double reciprocal again. Okay, you don't have to. You could actually leave it like this and solve for it, and that's perfectly fine. You'd find out mathematically it's the same thing. It's just that if you look it up online, if you looked it up in a biochemistry book, they would actually have it on the opposite. Like they would have they'll have theta on the top and 1 minus theta, and they'll have L to the top and KD on the bottom. Okay. And so that's what we're going to do right now, is we're just going to go ahead and take that reciprocal of it to make it theta over 1 minus theta is equal to L to the N over KD. Like I said, mathematically, you wouldn't have to do it that way. You could solve from it from the one in the blue. I'll show you. All it's going to do is it's going to change the shape of your curve. One will be looking like this, and one will be looking like that. Okay, now let's take the log of both sides. So I'll change colors again. So we have the log of the ugliness, my word. So in some books, if we would have left it alone before, it would have been a log of 1 minus theta at the top and theta on the bottom. That's why it doesn't really matter as long as you define it, is equal to the log of the right-hand side. Think back to the rules of logs. Right, the term. What happens whenever you're trying to divide or multiply things with and you're trying to take the log of it? Do you remember? You subtract. You subtract if it's dividing. If we were multiplying, it would have been added. Okay. But we're going to be subtracting. So now we would have log of the concentration of L to the N minus the log of KD. And then, as I mentioned before, the definition of a log is the log of something to a power takes that is the same thing as putting the power there. Since I'm not a mathematician, I don't know if that has a special name or not. So I'm just going to rewrite that. The log of the ugliness, my word, is equal to N times the log of the concentration of L minus the log of KD. This kind of plot is called a log-log plot, because you have a log of y is equal to the log of x sometimes. But we can already see it's also linear. So this would be y is equal to m times x plus b is a constant. Of course, it can be negative. Right? But it's a line. Okay. So if you plot it, okay, let's see. You're going to get something that looks like this. Whoops. Sorry about that. The slope is equal to n. Okay. Oh, and I forgot to put what the units or the things were. That's not good. This is log of ugliness. This is easy for me to say. This is log of concentration of L. Or if you're looking at substrate, the concentration of substrate. But the slope is equal to m. Or sorry, is equal to n. M equals n. And the y-intercept, the b, is equal to negative log KD. So this is one way to also get KD. That's supposed to be a D. Okay. But it turns something that would have been more complicated into a nice line. Once again, they call this the Hill plot or a Hill equation. So this is Hill. And that n is called the Hill coefficient. And it tells you a couple of things. Okay. One is it can give what's called the apparent stoichiometry, which would be the lower limit. Because you can imagine that if n equals 1, it means at least one thing binds. You can imagine, though, if you have two things that bind independently of each other at the same affinity, you probably wouldn't be able to, it would be hidden. Okay, that's why they say it's an apparent one. But if n equals 2, then that means you have to have at least two things for binding. Okay, that's why it's an apparent. If n equals 3, you have to have at least 3. N equals 4, you have to have at least 4. So on and so forth. But n can also be less than 1. So what does that mean? You went from biochemistry, you already had biochemistry, you went to hypothesize what would happen if n equals less than 1. And so here, and that's the real reason why they actually like to use, I'm going to scoot all of this over. So these are our three possibilities. We have n equals 1, n equals more than 1, and n equals less than 1. Okay. First of all, it's an apparent stoichiometry. But it's not that you can have, like if n equals 1/2, it could be that you have a half of the substrate binding or half of the ligand. You still have to have at least one. So what would that be? Does anyone from biochemistry want to hypothesize what that means if n is less than 1? It does have to do with cooperativity. What kind of cooperativity? Negative cooperativity. Is there anyone here, don't be afraid, raise your hand. Is there anyone here who doesn't know what I mean by cooperativity? Okay, great. All right, that's why I wanted to assume so. So cooperativity, what, if outside of biochemistry, what does it mean if something's being cooperative? It's working together, it's helpful. And so this idea, and this is what you're in biochemistry 1, they learn about positive cooperativity primarily. You can have positive and negative. Another term that they like to use, does anyone know what the other term was that they use? It's cooperativity, sometimes that they use, actually starts with an A. Allosteric. Or if they say something is allosteric, that's another way of saying cooperativity, okay? So hemoglobin is the textbook example. Okay, for biology, what does hemoglobin do? It binds oxygen. How many oxygens can bind in hemoglobin? Do you remember? There can be 4, up to 4. But it's not like a light switch, all or none. You know, it's not like you have 0 oxygen and then 4 oxygen and automatically bind. But what happens is the first oxygen binds and it makes it more likely that the second one, which makes it easier, that the third one, which makes it easier than the fourth one. So if you look at its binding curve, it actually looks like this. It's not only is it hyperbolic, but if you look at it, it actually is sigmoidal. Okay, that's what it's called. It's S shape, sigmoidal shape, which is also indicative of cooperativity, by the way. But that's what that means. It's positive cooperativity. So for hemoglobin, n is greater than 1. In fact, in theory, I think experimentally it comes out to about 3, but or 3.2 or something like that. But we know now that there's 4. But you can see there it's cooperative, and there's at least 3 that like to bind. In reality, there's 4. However, the same thing can also be true for certain things that's called negative cooperativity, which sounds kind of like an oxymoron, or negatively allosteric. And that's where the binding of the first one makes it less likely that a second thing will bind, or less likely that a third, or less likely that the fourth, and so on and so forth. And so then n will be less than 1. Okay. So, if n equals 1, it means a couple of things. 1, either only one thing binds, and so you can't have cooperativity anyway. Or 2, you have more than one thing binds, and they have no effect whatsoever on each other, and so you don't ever see them interacting, so to speak. Okay? So that's why they usually just say that means that if there's 1, there's no cooperativity, or no allosteric cooperativity. If it's greater than 1, it's positive allosteric or positive cooperativity. And if it's less than 1, it's negative. In my experience, the lab that I worked in, the times that we saw negative cooperativity usually had to do with metal ions. And I'm sure that there are, and it's just stuff that we work on, where maybe, something that bound zinc or something like that, and so it made it less likely, after the first one binding, less likely the second one bind or third one. But I'm sure that there are other examples out there. Positive cooperativity you see a lot. Hemoglobin is, like I said, is the textbook example. Myoglobin, what's myoglobin do in biology? Does anyone from biochemistry remember what does myoglobin do? If hemoglobin binds oxygen, myoglobin binds oxygen. Okay, so it's not. It's just in a different, primarily in your muscle cells or certain organisms that have more myoglobin than hemoglobin. But myoglobin only has 1 subunit, hemoglobin has 4. That's why hemoglobin can bind 4 oxygens, myoglobin can only bind 1. And so if you plot its hill plot, it literally comes out to n equals 1. There's only 1 oxygen bound. There's no cooperativity whatsoever. And so because only 1 oxygen can bind ever. And so, but then that's what this is. This is called the hill plot, the hill coefficient. It's used a lot, especially in the beginning, whenever they're first looking and trying to characterize something. they'll almost always want to do some type of hill plot or hill coefficient to see, is it cooperative, yes or no? Is it possible that you have more than one thing binding and interacting? So this is always a good first step. And so in my old lab, she would almost always ask us, so did you do hill plot? Like if we first started working with anything, did you do the hill plot? And you better said, yes, before I came to you. Of course I did hill plot. Not really, the first time you did, and she's like, you need to go in the lab and go do the hill plot before we discuss this further. And so, which isn't difficult. Usually you have the data there, you just have to put it into the computer system, right? Because usually we've already looked at that, we've got the fraction down, and we have concentration. So it's just literally, okay, now I've got to take the log of it, I've got to take 1 over that, or what have you, to look at it. Are there any questions over this? Any questions? I'll try to also find some other like real world examples and for us to work through this week or something to look at, say, okay, hemoglobin is the, like I said, it's literally the one that almost every biochemistry textbook will have to show this kind of thing. I don't know, let me see if I can, oh, whoops, a bit of time. Let's see if I can get this thing to hook up to the internet. Hill plot hemoglobin, because I'll show you, this is it, this is the one that I was wanting to see. Right here, oh awesome. So, I know this myoglobin, like I said, looks just like, so if you notice, of course, hemoglobin concentration units that they're using is partial pressure of oxygen. See, here's a lot of theta, 1 minus theta, a lot of ugliness, as I call it. With a lot of concentration versus a lot of ugliness. And this is the plot. They've done myoglobin. Myoglobin N equals 1. Only 1 oxygen bind. Hemoglobin, it's weird. See, you see this, and then you see you go up, and go down. And so it's actually got 2 different slopes. This is also indicative of the fact that it's got more than 1 binding site and more than 1, for those in biochemistry already remember, more than 1 conformation, like one's more difficult to bind and one's a little easier to bind. And so that's why the slope of this first part is N equals 1. Trying to get that very first one to bind is the hard part. And then once you get that very first one binding, it goes up and then it's easy to get 3 more to bind. So that's why overall it's 4. And so that's why this is the hill plot bit. To show you, myoglobin has no cooperativity. And then that one, hemoglobin has positive cooperativity. I don't know. Let's see. Come on, let me click on here. Sorry, it's really slow to try to. Negative. It'll plot. Let's see if it brings up a real life example. Images. I was looking to see if they had a real life example of one already, but I don't see one. And so that's why I say very rarely. It's not as common. But whenever it does happen, obviously that means it's very important. But okay, so the other term whenever you're not looking, well, we'll talk about that later. I was gonna say that the one whenever we did like the reciprocals, or if you do what's called like a straight, sometimes it's called the scattered plots. It's named after protein scattered. But okay, are there any questions?